This video is meant to accompany Chapter 5 of Introduction to R for Business. Now, in this chapter, we're going to go through and talk about variable assignment and operations. We're also going to talk a little bit about more complicated types of variables such as vectors, lists, and data frames, for example. Now, our mode of operating will be to basically go through each command line by line, talking about them, sometimes deviating from them, and going back and running a slightly different version. So there's two ways we can run slightly different versions of commands. One is we can go back up here and change the script and rerun it. Or anytime we want to run just sort of an ad hoc command, and we'll do this several times, we'll just click down here in the console and run from there. But let's start off by running commands in the script. Now, the way you run a command in a script is basically put the cursor someplace before the first executable line that you want to run, and then you press Control Enter. Now, what that does is RStudio goes through and says, okay, that's a comment, that's a comment. Ah, there we go, that's an executable line. So it runs that executable line. It then shows us that it's run that executable line by mirroring what it just did down here. Now, as we'll talk about in just a little bit, we're not actually seeing what's in X at this point. It's acknowledging to us that it ran the command, but to see what's in X, we've actually got to go look at it. And we'll talk about that in just a second. Right now, what I want to focus on is the idea of variable assignment. Now, in most other programs, and in Excel, and even when you do things by hand, you're used to using the equal sign for variable assignment. And usually, without any problems, equal sign will work in R. So that's what we see here. We've assigned a value of 7 to X, and we look over at the global environment, and we see that, sure enough, X contains 7. Now, what you're going to find is that when you do variable assignments like this, when you put something in a memory storage location, RStudio is going to show you it as well as it can over here. When you're taking one value, like we're doing right here, and assigning that to a memory location, it can show you what that one value is. But once we get to more complicated memory storage locations, once we get to situations where we're storing more than one item inside a named location, it's going to have to start summarizing that information. And you'll see what I mean later on in the video. Now, as I was saying, it's perfectly acceptable to use equals for variable assignment. But most people using R don't do it. And the reason is that we've got another command, which is the left arrow, created by using a combination of the less than sign and the dash or minus sign. That left arrow does exactly the same thing, right? So we see that the same way that we managed to store 7 into X, we've now stored 8 into Y. The reason that most people that use R like to use the left arrow for variable assignment comes about if you start looking at something a little bit more complicated. So I'm going to run a command here, and the command I'm going to run basically takes a function called LM, which sets up a linear model for regression, and then it tells that function something about the model that we want it to store. Here we're going to see that we're storing in what we want the formula to be for a regression, i.e. y to be a function of x. Now, we're not going to go too much into this model right now, but the point is that inside that linear model function or command, it's using the equal sign to indicate the assignment of a parameter. Then once we run that LM function or command, we then turn around and take the output from it and store it in a memory location called relationship. Now, a couple of things about this. First of all, as we look over here, we'll notice that the relationship variable that we just created is more complicated than just a single value. It's actually more complicated than just this formula that we've indicated over here in the script that we ran. We'll look at more detail in this once we have commands for doing that. But basically for right now, just realize that we haven't actually run regression. We've just set up a storage location where if we were to run regression, it would be able to store not just the results of the regression, but error statistics, fit statistics, and so forth. So we're basically setting a place for regression to be stored. But here's the issue that I wanted to talk about. We're using the equal sign multiple times here. We're using it to assign a parameter to values to a parameter inside the function, and we're using it for variable assignment. You can also have situations where if you had a logical test you might use the equal sign too. So given that we've already got several other things that we're going to use the equal sign for, why not do something like this, right? So here, we're going to use that left arrow for variable assignment. So anybody that uses this convention for writing their R scripts is going to look at this and say, okay, so this must be assignment of a parameter or identification of a parameter inside a function or command, and this is where you take that result of the LM function and store it into relationship. It gives you exactly the same thing as using the equal sign. It's just cleaner and neater. So from now on, if we want to assign anything into a variable or a memory location, as we sometimes call it, we're going to use that left arrow. Now, let's go back and talk about, and I'm just using Control L to clear out the console between steps here. Let's go out and talk about the fact that when we ran this command right here, right, it showed us that it ran the command by saying x equal to 7, but it didn't actually show us what was in x. That is, since it ran the command and it didn't give us an error message, we're supposed to sort of assume that it was successful in storing 7 in x. Yes, we can look at it over here and see that we've got 7 stored in x. But if you actually want to see what's inside a memory location or a variable, you do it by basically having it run that command itself. Now, so when I type x and then press enter, or when I simply run this line of the script by pressing Control Enter, it comes down here and it acknowledges that by saying, yes, there's a 7 in there. Now notice that in front of the 7, it puts a 1 in square brackets. Well, this gets into a couple of interesting things about the way that R and RStudio store things in memory locations. You see, we think we just stored one item into X. We think we put a 7 into X. We did, but R thinks ahead and says, well, the silly human might assume that it only wants to put one thing in X now, but I know that it might want to put more things in X later, because there's lots of situations that it's run into before where that happens. So what it does is it stores that value of 7 as the top thing in what's called a vector, which is like a stack of values. And when we ask it to tell us what's in X, the reason it's showing 1 here is because it's telling us, hey, I'm going to start listing all the things in X, and I'm going to start with the top. So that 1 indicates the first element of X is 7. Now, when we get to actually looking at vectors that have more than one thing in them, then we'll see that if we were to type the name of the vector, then R would display as many things as it could on a row, and then it would go to the next row, and on that next row it would start by listing in square brackets which element it was starting with. So basically that 1 is just telling us, hey, this row that I'm about to list starts with element 1, and if it were to do more rows, it would say what those rows are starting with. Now, this brings up an important point. The smallest set of stuff that R assumes it's going to store is always going to be a vector. That's the basic unit of storage in R. And so because of that, we're going to use that sometimes, and R was right. There might be cases where we want to go back and put more stuff into that memory storage location called X. But realize that anytime you store something, it's going to be stored as a vector. Now, what if we want to look at X and get a feel for what's in it? There's several useful commands that'll help us with that. The first one is class. Now, class tells us that X is numeric. What's class versus the next command, type of? Well, think of them as both categorizations, where class is sort of the upper level of ways it's going to group different types of variables, and then type is a subgrouping, if you will. So this tells us that X is stored as a numeric value, and more importantly, or more precisely, it's stored as what's called a double precision numeric value. Now, double precision numbers have twice as many digits as a single precision number. No, they tend to have up to a certain number of digits that you can have, and they're pretty darn big. Now, what this means is that when R stores what it thinks of as a number, it defaults on giving us sort of as much space as possible. It doesn't try to store it as an integer. It doesn't even have a default type of single precision. It sees a number, it stores it as a double precision number. Now here's another interesting thing to point out. For those of you who've ever programmed in other languages, before you can start storing things in memory locations, you're usually used to having to set it up. You usually have to tell the program, hey, I'm about to store something in X, and I want to make X capable of storing this kind of stuff, right? You don't do that in R. R basically guesses for you, and like I said, it tends to make sort of conservative estimates, giving you more space than you probably need. But it looks at the data you're passing it, you're trying to assign to a storage location, and it makes an informed decision about, hey, looks like numeric data to me, so I'm going to store it as numeric, and just to give the user as much space as possible, I'll store it as double precision numeric. Now, we'll see that if we store character strings, it'll put it as a character string type variable. If we store dates, it'll store it as a date type variable, and so forth. But the point is that we don't have to set up memory locations before we use them. We set them up in the course of using them. As soon as we reference one that doesn't exist, as soon as we try to store or assign a value to something that doesn't exist, then R looks at what we're trying to store or assign, and it sets it up for us. Now, one thing that I'd like to point out is a lot of you have had experience in Excel before. And in Excel, there's a function called len, and that tells you how long something in a cell in Excel is. There's a command in R called length. It doesn't do, if you're used to using Excel, what you think it does, right? If you run the length command, it's not looking at how many numbers or numerals or characters are in a particular storage location. It's looking at how many items are stored in the vector. So when we run the length of X here, what it's telling us is there's only one thing stored in X. Now, another command that'll come in handy once we start getting more complicated memory storage locations is attributes. What attributes normally does is it tells you metadata about the storage location. Metadata is a fancy name for descriptive information that isn't actually part of the data set, but is stored alongside it so you can get an idea of what it is. And we'll see that once we start storing longer data sets, for instance, name will be stored as a metadata item. Now, let's talk about a couple of other types of variables that we might want to assign. I'll press Control L to clear out the console. If we wanted to assign something specifically as an integer, we'd put an L after the value. See, when we do this, it stores y as an integer. And if we were to want to see what the type of y was, it'd also be an integer. So a couple of comments here. First, why would we want to store something as an integer? Well, double precision numbers take up a certain number of decimal places, a certain number of memory storage locations. Integers don't take up near as many. So particularly if you start sort of getting low on memory, and we'll notice along the way that R is a in-memory programming language. It assumes that storage locations you're going to use are up in random access memory. If you store millions of variables, possibly tens or hundreds of millions, at some point the size of each of those individual items that you've got in vectors starts to matter. So if you want to be parsimonious, if you want to slim down your memory storage, then storing something as an integer makes a heck of a lot of sense. Now, the second thing to bring up is, why are class and type of the same for this type of variable? Well, the folks that designed R knew that they were only going to set up a certain limited basic number of different types of variables, right? For numeric, they set up by default just double precision. For integer, they set up by default just integer. Other types of languages have single precision, which we talked about. They also have things called long integers that need a little bit more space. The folks that designed the core R made it possible for other folks that write add-on packages to R to make their own types of variables. Now, they want them to fit sort of in the classes that the creators of R designed, but they're perfectly willing to let them make their own classes if necessary, or more usually, to make their own types of variables. So it's possible that somebody that had a package and they wanted to have long integers would make a long integer type of storage location that would be integer class, and maybe they would call the type of long integer. Now, that's real handy if you can go back and actually put L's at the end of all the values that you're bringing in or that you're inputting into R. However, and let's do Control L to clear out, how do you deal with it if you start with a more likely situation, which is you bring in a bunch of numbers from the outside, for example, and then you want to go back and convert them to integer? Well, let's suppose that we stored y, and now y is not being stored as an integer. Now it's back to being stored. And if we did class and type of, we'd see that because we just said put 8 into y, R defaulted to putting it in as a numeric double precision number. Well, there's a couple of very handy functions or commands in R that start with as dot. And here's an example of one of them. I can run as dot integer on y, and then it turns around and takes the result of that and puts it back into y. Right? So this is another reason, by the way, to talk about variable assignment. When you use a variable in the right-hand side of an assignment expression, R does the stuff on the right-hand side of the arrow first, and then that allows you to take that result and sort of store it right back in place. So again, trying to be parsimonious of use of memory, you're not going to create a temporary working variable. You're going to take what's in y, you're going to do something to it, and then you're going to store it back into y. And that's exactly what we did here. Now, what does the as.integer do? Well, it takes numbers that aren't integer and it converts them to integer. So that took the double precision value for y that we had before, converted it to an integer, and then stored it into y. So now if we go back and look at the class and type of for y, it is now integer. We'll see these as dot commands used a lot for changing the type of variable that we've got. We'll also see an associated set of commands or function called is dot commands that basically are logical tests that ask the question, is this an integer, or is this missing, null, or something along those lines. Now, so far we've been clearing the console by pressing Control L. I'm going to show you a different way. And actually, we're still going to press Control L. It's just we're not going to do the pressing. We're going to let the program do it for us. There is a command in R called cat. And what cat does is it basically takes whatever string that you pass it, and it displays it down in the console. So for example, if I went back and added a command here, cat hi, like that, and then ran this, it's going to not just run the command, but it also then takes what's inside the cat command and it displays that in the console. Now, we're going to use that, but we're going to use that in sort of a special way. If inside the double quotes inside the cat command, you put a backslash, like I'm doing right here, that backslash is what's called an escape character. And it's basically telling the cat command, hey, wait, I don't want you to type what I'm about to type after this. I'm about to give you a code for either a certain key press sequence or something special. And it turns out that the ASCII code for Control L, which clears out our console, is 014. There's lots of lists on the internet of the different ASCII codes, right? And basically what you have to understand, the way a keyboard works, you press a key, there's a code for that. You press a combination of keys, there's other codes for those. So Control Alt Delete, for example, or Control L in this case, is one code, even though you're pressing multiple keys. So what we're going to do is we're going to use the cat command to send the control code, if you will, for Control L to the keyboard. So I run this command, and it clears out the console. Now let's talk about storing character values into memory locations. Let's take my name inside double quotes and store it into name. Now, because I'm passing something with double quotes around it, R sees that and assumes that we want to store it as a particular type of variable. And in fact, if we run class and type of, it tells us, that's character. And just as with integer, class and type of default to the same thing here. They're both character. Now, if you look over to the right in the global environment, it tells you you've got a variable called name, and inside it, it has value Troy. And it indicates to us that Troy is a character string by putting double quotes around it. Now remember, as we talked about before though, this is not like Excel. If you run the length command, it's not telling you how long Troy's name is. It's telling you how many values have been stored in the name vector. In this case, again, we've only stored one value, so the length of the name vector is 1. Now, we'll clear out the console again. Let's talk about logical storage locations. If you pass T or F or true or false without quotes around it into a variable, that gets stored as a logical. It's both a class logical and a type of logical. Now, you can think of these as true or false, or you can think of them as true equals 1 and false equals 0. There's lots of commands that use that. And the reason sometimes to use this kind of logical storage location is it really only takes one bit. It takes, if it's true, it puts a 1 in that bit. If it's false, it puts a 0. So these are sort of the skinniest, if you will, type of memory storage locations. Now, we've already talked about how to store integers, right? Right now, we've got 8 in Y, and its class and type is integer, because remember, we use the as.integer command to put it in there. So we've covered integers. We'll move on past that. Let's talk about storing and using dates. Now, there's several built-in date functions in R. The simplest is date, open and close parentheses. So what we're doing here is we're taking and running the date command and then taking the result and putting it into a memory storage location we're going to call date time. Now, if we look at date time, we'll see that it's a character type storage location, and it's a type of character. That is, all this date function really does is it gives us, and if you look over here to the right, or if you simply type the value date time here and have it display it, it basically takes the date and time that the system has and it stores it as a character value. So this is not the kind of date time expression that we can do math on. I can't take date time and store it, and then I can't take date and store it, and then a couple of minutes later run date again and then take a difference. It would be the difference of two character strings, and R would say, I don't know what you want to do. So you have to think ahead. If you just want a human to be able to look and see what time something was run, use the date function. But if you actually want to start doing things like math and how long did something take, use, for instance, the sysdate command. Now, a couple of comments here. First of all, this is going to result in something that is a date type variable that is stored as a double precision number. Now, in the book, as described, I think that R measures dates as the number of days elapsed since, I think, January 1st, 1970. Now, how it stores it in the back of its mind and what it shows us are two different things. So if I go through and say, hey, I'd like to see what's in date right now, it comes back and shows the human today's date. So I'm making this on March 31st, 2020. But we already said that it's stored as a double precision number. So just like, and if you're familiar with Excel, Excel stores dates in one manner, but shows them to you in another manner. Same thing here. R shows dates in one manner, and we should notice that not only is it not including time when we do this date variable, but it's also not putting quotes around it, right? So it's showing us what it thinks we want to see, but it's actually storing it as the number of days from sort of a basic starting date inside the R system. Now, you can use this then to do math. So for example, I'm going to run this command right here. Now this command right here does several different things, and I want to talk about them sort of in turn. First, I ran the asDate command. Now, just like the asInteger command, asDate takes, in this case, character value and turns it into a date value. So when I run this on the character string year dash month dash day, surrounded by quotes. It takes a character argument and then comes out with a date, right? So that'll tell us the number of days since January 1st, 1970 up to January 1st, 2000. Now, we also run the sysdate command, which tells us the number of days since January 1st, 2000 up till today. And you're like, okay, wait, why do it? Well, you'll see this in a lot of programming languages. And the whole reason that R uses a base starting date, Excel uses a base starting date, is normally we don't really care how many days a certain date is from January 1st, 2000. But when you take the difference in two dates like this, the January 1st, 1970 goes away, right? Think back, and I'm going to type something here on the screen, even though it's not something we're going to run. Think back to when you were learning the basics of, oops, not what I meant to type there, the basics of algebra. Now, a minus b minus parentheses c minus b simplifies, right? And you got to dig way back to your algebra time to this. The reason is you've got a negative b minus a negative b, so the b's cancel out. That's sort of what's happening with these dates here. You've got today's date minus, or expressed as, the number of days since January 1st, 1970, minus the difference between January 1st, 1970 and 2001, January 1st. So in this case, the basing everything on January 1st, 1970 is the equivalent of the b's in this expression down here. Long story short, when you run this, right, when you say sysdate minus asdate 2000-01-01, you're going to wind up with the number of days between today and January 1st, 2000. Now, why am I passing through all of that through an as.double command? Well, just to be doubly safe. I'm going to assume that most people reading this book and watching this video are, doing this probably in the 2020s. So this is going to give us back a number that's going to express the number of days in a 20-year period. But who knows? This book, this video might be around 40 or 50 years from now. And in which case, you might be getting close to the point where, just in case it takes and tries to spit out an answer as an integer, I want to make sure it has enough space to show the whole answer. So I'm just being sort of belt and suspenders safe and saying, let's show the answer, or let's store the answer as a double precision number, just to give us as much space as possible. So when I run this, and then I look in what's in age days, or I could look over here and see it, obviously. That tells us that as of today, and today is March 31st, 2000, there have been 7,395 days since January 1st, 2000. Now, and I'm going to do a mathematically terrible way of converting that to years. I'm not going to take into account things like leap years and everything. I'm just going to divide that number of days by 365. So if I do that, then we see that age years, which is close enough for what we're doing, is about 20 and a quarter. So somebody, for example, that was born January 1st, 2000 would be about 20 and a quarter years old right now. Now, to be honest, will you ever use sysdate? Sure, but not that often. What you will use, and what we'll use a lot in the next chapter, is the next thing, systime. So let's take and store the current system time into a variable called time. Now, if we look at that, we're going to see that it looks like a date-time group, right? So one of the secrets about storing time is, even if you're going to use it intuitively the same way that we just did with sysdate, that is, you're going to store time now, let something happen, and then see what time is after that minus what the stored time was, i.e. see how much time was elapsed. You got to worry about, well, what if the clock wraps around, for instance, midnight? So you really need to store which day it is in addition to what time it is, in case you wind up having to do a time difference between before and after midnight. So in the manual for R, it describes how this excuse me, systime command runs. It basically is storing the number of seconds since your system started up. Now, it stores it as a particular type of variable, though. It's called a POSIX-CT. And what this does is it's a number of seconds since something happened type variable. But more importantly, if the silly human asks about it, show it to them as a date timestamp. So it's stored as a double precision number of seconds since something has happened. Now, if we were to want to use this as a timer, and we will in the next chapter when we're importing files and seeing which different command works better, what we would do is at any point in time we'd say, okay, right now, I wonder how much time has passed since I stored systime, right? So we've been doing something between when we stored it and when we just accessed it again. And this shows me that it's been about 2.05 minutes since I ran that. So there's some pretty sophisticated analysis and sort of parsing that goes along with storing things as that POSIX-CT. When you ask for how long has it been since something has happened, if it's been a few seconds, it'll tell you what the time difference is in terms of seconds. If it's been, as here, I was talking for a couple of minutes between when we first stored systime and then when we accessed it again just there, it was a couple of minutes, so it expressed it to us in terms of minutes. Now, I'm going to go ahead and end the Chapter 5 video there. This will be part 1, just in the sake of making it sort of digestible. We'll come back in and start another video with operators in just a second.